Hey, good morning, everyone. My name is Troy Martin. I'm going to be giving a talk about the efficiency of Wi-Fi, doing a little bit of analysis both on the wired and the wireless side, just to compare and contrast those two. Okay. So before we get started, I just want to tell you a story. Years ago, there was a group of hyper-intelligent, pan-dimensional beings that demanded to know the ultimate answer to life, the universe, and everything. Okay. So they went through a bunch of calculations. They tasked a computer called Deep Thought to come up with this answer. It took Deep Thought 7.5 million years to crunch through its calculations, do its verification, because you should always validate, and it came up with the answer 42. Okay. After that, Deep Thought told the beings that the answer was probably meaningless to them because they didn't know what the question was. So the beings asked Deep Thought to come up with the question. And Deep Thought responded that it could not. But it could help them come up with the designs for a new supercomputer that could come up with the ultimate question. And this new supercomputer would use intelligent beings as part of its computational matrix and come up with the ultimate question. Now, it took the new supercomputer roughly 10 million years to come up with the answer to this riddle. Unfortunately, the supercomputer didn't have access to Cloud 2.0 or the hyperelasticity of cloud-based technology that 5 minutes before coming up with the answer, it was destroyed. And so we never actually discovered what the ultimate question was. Now, I'm sure many of you in this room can relate to this. When you have customers that ask you to produce the ultimate answer to the question, how far can this AP cover? How many clients can connect to this access point? Or what will my throughput be for all of my users? Okay. I also want to add on this a little bit where I think we can optimize some of our efficiency on Twitter. If you guys have dived into the mythology of the number 42, if you looked at an ASCII chart and you looked up the decimal value for 42, it translates to the asterisk, right, which is the wild card. So I'd like to propose that going forward, anytime we need to shorten, it depends within our answer, but we can just throw in 42 and save ourselves some characters. Okay. So a bit about me. Again, my name is Troy Martin. I went through university, did electrical engineering and computer science. But I took a lot of electives. I was super close to a philosophy degree. I was one term away, but I decided that it'd probably be good to get a job and make some money. I come from Canada, so hence the 802.11a. So Brendan Martin, from Saskatoon, Saskatchewan, which is actually where I went to school. But he put together that logo. And I did a lot of teaching down in the US, and we talked about the different protocols, 11A, B, G, N. And down there, they thought that I was speaking Canadian every time I said 11A. They didn't realize I was actually talking about the protocol. Okay, so a little bit about Ethernet. We'll talk about that just to put things into context. So you guys are all familiar with the CSMA CD. So the CD bit in Ethernet, that takes into place when there is a collision. So there's a guaranteed collision at this point. We know that we have to take action to try to revert out of that process. We're not guessing or making this up. So Ethernet has a definite win there. Ethernet is also full duplex, so the ability to transmit and receive at the same time. I would argue that this is a defining characteristic of something that's switch-like, okay, to have this ability. Okay, there's also a fixed data rate. So whether you're doing 10, 100, or 1,000 gigi interfaces, it's a fixed data rate, it's constant, it will not change. Okay, it's locked in. If you want to move from 10 to 100, you upgrade your infrastructure, or you change the configuration setting and enable that globally across that segment. Okay, it's also a confined medium. Okay, the Ethernet pipes, essentially they're waveguides for electrical signals to propagate through them. You can also get shielded Ethernet cabling, which helps protect it from interference and other sources. And of course, you have the 5, 4, 3, 2, 1 rule. Okay, this is, you have 5 different segments, only 3 of which can be transmitting, and so on and so forth, all these different numbers. Okay, so let's take a look at the Ethernet frame. So in its simplest form, you have an Ethernet frame that's between 64 and 518 characters with 4 bytes of a CRC header. Okay. Also in front of that, you have 8 bytes of preamble and 12 bytes of interframe gap. So the preamble is just a series of bits to help synchronize the receiver as the signal's coming in to be received. And then you have this gap that's in between the frames. It's locked at 12 bytes. Right, so in 100 meg, or sorry, in 10 meg Ethernet links, this was 96 bits, or it'd take 9.6 9.6 microseconds for this to kick in. And the reason for this is that's how long it needed the receiver chipset to flip between transmit and receive. Right, so back in the day when Ethernet first evolved, that was built in just to allow the electronics to flip and roll over. But that 12-byte frame is carried over as we evolve to 100 to gig Ethernet links. But we've reduced the time by a factor of 10 through each iteration and evolution. Okay, and if we expand out the Ethernet frame, we have the payload and the Ethernet header, which consume some of the information. So if we do an analysis on the efficiency of that, the efficiency is what's actually delivered in the payload. Everything else is overhead for the Ethernet frame. And then optionally, if you're doing .1Q, so if you have distributed data planes in your networks, there's a 4-byte header for the .1Q. Then if we step back for a little bit, in 1638, Galileo proposed an experiment. He wanted to measure the speed of light. So he sent one of his buddies up to the top of a hill and another buddy to a hill a long ways away. And one guy was supposed to turn on his lamp, and the other guy would measure how long it took before he saw that. So it turns out that light travels much faster than they were able to measure, and what they were really measuring was human reaction time. But this picture here, this is from a mountain just outside Calgary in Canada. It's the Three Sisters mountain range. But why I wanted to put this up there is just to talk a little bit about light and propagation. So in gig Ethernet links, it takes 1 bit can travel about 0.2 meters at gigi rates. So 1 bit is extended for about 20 centimeters. Right, so every 20 centimeters, you have another bit passing through the wires. With wireless, because it's electromagnetic radiation, as it's sending its waves through space, in about 30 centimeters, light will travel 1 foot. Right, and if you start thinking about short guard intervals, which is just the gap between symbols that are sent across your airwaves, the long guard intervals are 800 nanoseconds, so light can travel about 240 meters just within a guard interval. Right, so in that 800 nanoseconds, light's gone 240 meters. Okay. This is a packet capture that I just collected this morning. So just a quick scan. Basically, I did some analysis on the size of the frames. And you guys are probably aware, but again, some real-world examples of this. The bulk of your traffic is sub 256 byte frames, right? So there's very small frames going across your airwaves, which ties into your efficiency. To get high efficiency, you want to send as much of your data payload as possible. But if the bulk of your frames going across your networks are only 256 bytes, you have a fair bit of overhead that's going along each of those frames that's being sent 256. So this is just a comparison for Ethernet. If you're looking at this, so at 46 byte payload, which is the lowest you can get, we're looking at 52% efficiency with all that overhead, right, which isn't very high. But if we stuff those frames as big as we can get, we're pushing near 100% efficiency on the wired side. But if we look at the bulk of our traffic being 256 bytes or less, we get about 85% with Ethernet, okay, which just a number to keep in mind, okay. Now, don't panic. I know this is a wireless conference. This isn't all about the wired side. So we'll dive into wireless now. Okay, so we'll compare and contrast. So we talked about Ethernet. Its collision detection kicks in when it knows there is a collision. So it's super hyper efficient until there's a collision, and then it takes action. With with Wi-Fi, we're always trying to avoid the possibility of there being interference, right? So every frame we send, we take proactive action to avoid the potential for interference, which introduces immediate efficiency loss. We're also half duplex in Wi-Fi. So again, this is something that I'd characterize as a defining moment for something that's switch-like, is you can only transmit on a given channel. Only one device can transmit on that given channel at any given time. If 2 devices are on the same channel transmitting, you have interference. Okay, regardless of how you carve up the spectrum. Okay, and this has implications for 8 to 11x, AX, sorry. You also have a variable data rate. So the high efficiency, you want to transmit at high data rates. But as we move away from the access point, or we have interference from other devices, or reflections off walls, different objects, we shift in those data rates, which impacts our efficiency. So we have significant loss that can be a result of that. It's also an unconfined medium. Right, we're always vulnerable wherever your receiver is. If it happens to be in an area of interference, it degrades the signal and can introduce retransmissions. If we have to send the same information again and again and again, obviously that takes away from our efficiency. Okay, so now if we break down a Wi-Fi frame, and so this is a super simple example. I'm going to take you guys back to the days of 802.11a, the letter A, not A, like in Canadian speak. I'm also going to talk about the lower data rate. So we're going to talk about 6 megabits per second. So it's kind of a worst case example for some of these numbers that are up here. And if you guys are keeping up with technology, you could also call this Wi-Fi 1 for the purpose of this slide. Okay. So in this slide here, we have the 802.11 frame itself. So the MS or the MPDU, the MSDU is limited to 2304 bytes, and if you translate that down into 6 megabits per second speak, that takes about 3 milliseconds for that frame to be lobbed up through the airwaves. But on top of that, you also have some signatures and preambles. Right, so again, this is training your receiver, getting it calibrated to receive the signal coming in. So that adds some time. So you get about with the signal and the preamble, another 20 milliseconds. And then every unicast frame that you send, there's a small gap, that SIFS interval, which for 11A is fixed at 16 microseconds. And then the acknowledgement. Now I've simplified the acknowledgement. The acknowledgement frame itself would have a preamble and a sig on it as well. I've just shown it as one, but with the sig and the preamble, your acknowledgement would take about 44 microseconds. Okay, just as a question, does anyone know what the duration value is in an acknowledgement frame? What that's set to? In a frame, it's set to 0, right? Right, exactly. What about a block acknowledgement? So a group of acknowledgements all stuck together. It's 0 as well. So the duration is always set to 0, but it does take time to send those through the airwaves. And then following the ACK, there's a diffs interval. And then before the next frame can be sent, or before this frame could be sent, there's a contention window, right? Which could be a number anywhere between 1 and 1023, depending on how many retransmissions it had. So you're looking at anywhere between 9 and just over 9,000 microseconds, right? So you have potentially, worst case scenario, you have your client with frames ready to transmit, and it's waiting 9 milliseconds before it can send that frame, right? So there's empty airwaves. It's just waiting for its counter to tick down, okay? So this is just a little slide, a reference for you guys to understand, as you walk away from the access point, your data rate shifts. Okay, and we'll talk a little bit about modulation schemes. So each symbol that gets sent out with OFDMA, each symbol with long guard intervals takes 4 microseconds to pass through the airwaves. So the data bits themselves, it's about 3.2 microseconds, and then you have the 800 nanosecond guard interval. So you're looking at about 4 microseconds for a symbol, which allows you to send about 250,000 symbols per second. All right, so now if we apply that to this table that we have here, and so these are taken directly from the 802.11, the 2016 standard. So it's one of the tables that are in there. But within a single frame, so again, if we look at 6 megabits per second, that symbol could have 48 subcarriers. But we're using half coding, right? So of those 48 bits that we're sending, half of those code bits, it's just error protection, right? They're just to make sure that the data is sent there properly, right? So only 24 of them are valid data bits. So we take 24 data bits and we multiply that by 250,000, that's where we come up with the 6 megabits per second. That's where that data rate comes from, so you can work through the math and keep going through the table. Okay, we can jump this up to 11N. Through in this, so we're looking at so this is just 11N, so it's a little bit more efficient with the technology. So we have more subcarriers, right? We've gone away with some of the sidebands. And then with 11AC, so we've also changed this, so now it's showing 3 spatial streams, so you can see how the bandwidth is going up. So we get more efficiency, but when we transmit that data, we can be sending it at any one of these different rates, right? It's not always at the highest rate, so we are losing some efficiency as a result of this, okay? Now this slide's a little bit more interesting. This is what things could look like as we strive for high efficiency. So if we move to the 802.11ax world, this is what it could look like. So if we look at the top row, we only have six carrier streams, or 6 bits of data that we're using. So in this example, and Perry is going to talk about OFDMA in one of his presentations, so he'll go into a deeper dive with this as well, and I believe Mark is talking about 802.11ax, whether it's dead already or not. But I just wanted to throw this table up and just talk to this a little bit. And so they'll kind of build up the story going into this table, but we're looking at something that's 26 tones. So it's 26 RUs in this table. And if you subdivide your channel into the smallest chunk possible with 802.11ax, your data rates are 400 kilobits per second, okay? So you can have multiple clients talk at the same time, but they're only talking at 400 kilobits per second. So this goes back to kind of the comment that was made about something being switch-like. You can only have one device on this small chunk of the spectrum talking to get this 400 kilobits per second. You have many devices that talk at the same time with 11AX, but they're not all using the same chunk of the channel. Okay, each one gets their own slice of the pie. But I just wanted to put this slide up there just so you guys can soak in a little bit of what the data rates that are potentially coming with AX. So when we start stuffing multiple clients all talking at the same time, we're looking at, again, data rates, not effective throughput, but data rates of 400 kilobits per second, kind of worst case. Okay. And this is a reference slide. I used this when I talked about the frames earlier of where that 16 microseconds came from. You also have the slot times. So keep this number in mind, slot times of 9 microseconds. And these numbers change a little bit, whether you're like super legacy, old school 11B, or if you're moving up towards 11N AC type technologies. Okay. Now I had the pleasure of sitting in one of the Ekahau training classes, and Keith introduced me to the game. I used to call this arbitration, or contention, something more complicated. But I like the game. It's probably a Wi-Fi approved name. It's simple, keeps it. But anyway, I went back home. And I bought 2 bags of gummy butterflies, right? And I was gonna get my kids to play this game. They were super excited. They wanted to know the rules of the game. Like, you don't need to know the rules. I'll explain it when we play. Well, we had 2 bags of these gummy butterflies, and they were super excited. I thought it was gonna be fun and fantastic. So I poured the gummy butterflies into a bowl. We rolled the dice, and I have 3 little kids, so they're 12, 9, and 6. And they rolled the dice. They started backing off and walking up to the steps. And my youngest daughter, so she's 6, and there's only three people, right? So 3 clients. My youngest one had 3 collisions right off the start. Her brother and sister were eating gummies, and she didn't get any. And by the time the 3rd collision arrived, her face wrinkled up. She started to cry. Immediately, I switched into PCF mode, started allocating. Allocating butterflies on demand as my clients needed it. Okay, but if you want to really play the game, sign up for one of the Ekahau training classes. Okay. We also have the contention window. So I want you guys to kind of keep these numbers in mind as we go through the rest of the slides. The top chart, that's more before QoS kind of kicked in. So these are contention windows that you had. The bottom chart is when QoS kicked in. So basically, QoS gives you a higher probabilistic likelihood of getting access to the wireless medium to send your data. It's not a guarantee to send it. You just have a higher likelihood of being able to send it. But that leads us into the birthday problem. And so with the birthday problem, basically where this came from is you take a room of this size of people. So we have roughly 200 so people. 110. Okay, sorry. So imagine everyone in different states. You take this, so in a room with that many people, how many people in a room like this would have the same birthday? Okay, and what are the odds of those people having the same birthday? Okay, so the birthday problem is what is the probability of those 2 people having the same birthday? And then in a room like this, you're probably looking at at least a 50% chance of those people having a birthday. And so when you think about that contention window from the chart that I just showed you, every time there's a retransmission, or every time I want to send a frame, I pick a number from one of these columns here. So the first time I try to transmit, I'll pick a number between 1 and 15. If there's a collision, I pick a number between 1 and 31. And so it gets bigger and bigger and escalates, right? So it becomes a larger pool of numbers, kind of with the thought that if there's a bigger pool of numbers, there's less likelihood that devices will pick the same number and will avoid collisions. Well, if we apply that birthday problem to this, and if we look at this, so in the middle column, basically what happens if we pick the voice grade QoS settings, right? So we're picking numbers between 1 and 3 to transmit our data. If you only have 3 different numbers you can pick from, what are the likelihood that 2 of those stations will pick the same number? Okay, at 3 stations, you have at least 63% chance you're going to have a collision. If we move over to the left-hand column, so on that collision, now we're picking random numbers between 1 and 8. At 4 devices, we have a 60% chance likelihood that 2 devices will pick the same number, which is a guaranteed collision for those devices. And if we keep working this out and expanding it, if we go up to a contention window of 16, at 5 devices, we see the 50%. Okay, if we expand this out again even further, at 32 devices, it's only 7 devices, right? So we have a contention window of 32. It only takes 7 devices for 2 of them to have a 50% chance of picking the same number, which again guarantees a collision. And we keep rolling this out, and we can expand this. So this is a contention window of 64. If we take this up to the worst case, right? So contention window of 1024, at 40 devices, we're seeing a 50% chance of there being a collision. So if you have 40 clients connecting to your cell, and they're all, they all increase their contention window to be 1024, and they all have data to send all at the same time, at 40 devices, there's a 50% chance 2 of them pick the same number in a massive window of 2 to the 10. Right, so I think that's a quite high likelihood of a collision. Now, this is kind of obfuscated because you're not going to have a collision every time in all the devices, all jumping to 1024. Some devices might have a retransmission. They'll start counting down their timers while other devices are counting down. So not everybody's jumping up to 1024. But if you have a really poorly defined, poorly performing network, you could have a situation where all of your clients end up backing up to that 1024 contention window, where even at that size, there's still a good chance that they're picking the same number and still colliding if you have at least 40 clients in your network. Okay, and this really contributes to the inefficiency that you see in wireless and Wi-Fi. Okay, I also mentioned earlier that Wi-Fi is an unconfined medium, right? So it spews out into the airwaves. Now, the waves will propagate through space. So if you imagine the surface of the water, if you tap the surface of the water and your waves propagate through, you can tap another spot on that water and the waves will interfere and they'll cross each other. But where it really matters is where you receive that signal. They can pass through interference on the way to get to you, but where really comes into fruition is when you receive that signal. So if you're kicking the ball in from the corner kick there, and you've lined up that ball just right, what really matters is, are you getting the ball to that receiver? Is he able to bounce it off the head and get into the goal? That's what really matters, right, on the receive end. So you need to make sure that environment is clean. Okay. So some things you can look at as part of your design methodology. Primary coverage. You want to make sure that you have a signal, right? If you don't have a signal there, everything's off. Right, you have zero efficiency if you can't even get a signal there. Okay, if your design requires it, you can start looking at things like secondary coverage. Make sure you have that, and then to improve your efficiency, to make sure that's working well for you, you want to make sure that you're avoiding interference. Okay, so interference at the receiver, making sure it's getting a good clean signal so it can transmit at those higher data rates. The higher data rates that you're able to transmit, obviously the less time it takes you to lob that ball through the airwaves, get to receiver, and the more likelihood that you're not having to retransmit and to send the same amount of data over again into your environment. Okay, and then look at capacity. Now that I have a signal there, am I getting the right capacity for my targeted users? Am I hitting those goals? and if I'm not, obviously I need to have another conversation with my customer or reset expectations. Okay. So again, don't panic. Follow your good design methodology, and you'll be able to deliver a high efficient network for your designs. Okay. So as just part of a wrap up here, I'm a little bit ahead of time. But as part of a wrap-up for this, again, there's a lot of variability. I was going to try run through some complicated math, but it'd be specific to exact scenarios. If this happens and that happens, and the moon is at just the right angle, and everyone had the goulash the night before for supper, we'd see exactly 74.8% efficiency in this specific scenario. But of course, because of 42, we can't do that. So roughly, you end up with the Wi-Fi efficiency of somewhere between 50 and 70%. Obviously, the client devices will try to transmit as fast as they can between their negotiated access point to get those high efficiency values. But probably more important when you start having discussions is ask the right meaningful questions. Okay, ask the ultimate questions so that you get the ultimate answers. So you can build that in your design and get the most efficiency out of your network. Okay, and on that note, I just want you guys to remember 42 is the short end for it depends. And so long. Thanks for all the fish.